time? Yes.
Yeah. Right. I think, yeah, it's time to get started. Hello, everyone, and welcome to the first online seminar for 2021. My name is Panos Gastis. I'm the chair of the organizing committee of the Arena seminars this year, and I'm going to be the host of today's seminar. For the people who may not know me, I'm a postdoc at Los Alamos National Lab in the US. My research focuses on measurement of nuclear reactions relevant to supernova and stellar nucleosynthesis, as well as fission mass yield measurements here at Los Alamos. Today we are very happy to have as a speaker Dr. Anders Jerkstrand. Dr. Jerkstrand is an associate professor at Stockholm University in Sweden, from where he also received his PhD back in 2011. Between his PhD and his current position, he also worked as a postdoc at Queen's University Belfast, as well as he was a Marie Curie Fellow at Max Planck Institute for Astrophysics in Germany. He's an expert on modeling light curves and spectra from supernova and kilonova explosions, and he uses that for determining things like nucleosynthesis yields, and also for understanding underlying physics behind these massive explosions. Just a quick note before we jump to the presentation. I would like to kindly remind you to keep your microphones muted during the talk, so we keep the background noises low. And if you have any question during the talk, feel free to ask either by using the raise hand feature or by typing your question in the chat, and I will transfer the question to the speaker, or you can also keep them for the end where we'll have some time for questions. So, Dr. Jerkstrand, whenever you're ready, you can take it away.
Thank you very much for this introduction. So I will see if I can get my screen sharing set up here.
Yep.
Just a second. Okay, I hope you can see that fine.
Yep.
So we get started. So thanks very much for inviting me to speak here today. I will talk about how we try to determine the nucleosynthesis yields of supernovae by looking at their spectra, and in particular in the nebular phase a few months after the supernova has exploded. That's the phase when we can see into the sort of interior regions where most of the nucleosynthesis has occurred. So the outline of my talk looks like this. Start to give you just a very quick overview of supernovae and some basic points about their nucleosynthesis. And then a few slides about how we do spectral synthesis modeling and general methodology in trying to determine the yields that one can infer from observed spectra. I then have three applications that will serve to sort of illustrate some different things that one can do with this kind of work. So I will not go very deep into any one of them, but mainly focus on the results and see what those results mean in a broader context of trying to understand stellar evolution and supernova explosions better. The first application we'll look at is related to diagnosing oxygen production. The second one is to diagnose explosive burning yields, in particular the ratio between nickel and iron produced in supernova explosions. And the third one is a very recent result we have where a large amount of iron has been identified in a superluminous supernova called SN226GY, and this seems to point in a rather unexpected interpretation about the origin of this supernova. So you all know what supernovae are. It's the explosion of stars, and we have two different types to deal with. The first type is the core collapse of a massive star, and the canonical number we use is to say if the star is more massive than about 8 solar masses. But in fact, depending on stellar evolution physics, it could be 7, could be 9, could be 10. but 8 is the number that one typically uses. These stars, they will go through all the different nuclear burning stages and finally produce an iron core at the center. And this iron core collapses to a compact object. And in this process, the outer layers are blown out. Now, these supernovae, they come in many different subtypes. And it's mainly the presence of hydrogen, presence or absence of hydrogen, that determines whether it's a type 2 or a type 1 supernova. And you have type 1b if there is no hydrogen but helium, and 1c if there is neither hydrogen or helium. The interpretation being then that the progenitor star has somehow lost these outer layers at the time it exploded. The second supernova type we have are the type 1As, and these are the thermonuclear explosions of white dwarfs when they accrete matter by a companion star of some kind. And if they reach a critical temperature to ignite the carbon and oxygen, you have a runaway process and the whole white dwarf explodes. So the talk today will be quite focused on nucleosynthesis, production, and diagnosis. So one can broadly see nucleosynthesis in supernovae as occurring in 2 different processes. And what you see here in red are the layers where the elements are produced mainly during the star's life, normal life. So you have hydrogen burning, helium burning, carbon and neon burning. And the elements that are produced by these processes, they are believed to be ejected more or less as they are when the star eventually explodes. So we can call these hydrostatic burning yields. If we can diagnose these kind of yields, we can learn something about the stellar evolution of the star. If you go to heavier elements, it turns out that they are produced in the supernova explosion itself, and that's marked by this blue region in the diagram. So here we start in an innermost region by explosive silicon burning, which produces iron group elements. And this is happening in the wake of the shock wave that goes out. And initially we are over several billion degrees, and that allows for production of iron group elements. A little bit further out, the shock wave has cooled, and instead of silicon burning, we have oxygen burning that produces silicon and sulfur. And then it turns out, at least according to most standard explosion models, that we don't really get further explosive processing. So the combination of density and temperature in the shock doesn't allow for explosive carbon and neon burning, for example. So this is a good picture to keep at the back of the head when we are looking at spectral signatures. And basically you are probing 2 different things depending on whether you look at the lighter elements or if you look at these heavier elements. So in the talk today, I will show some results for 4 different elements, oxygen and magnesium, which are mainly produced by carbon burning, and it's a hydrostatic burning ash then. And we will also look at iron and nickel, and that probes down this very innermost region of the explosive burning. Here are the 15 most common elements we have in the universe. And the 3rd column here shows you where we think they come from. As you see here, core collapse supernovae, the first type of supernovae that we looked at, it's quite prevalent here. And indeed, most of the elements in the universe that were not made in the Big Bang are believed to be made in core collapse supernovae. At least up to approximately atomic number 40 or so in the periodic table. When you go to heavier elements, we have R process and S process, and you have also, for example, neutron star mergers coming in. Now, it's not particularly controversial, these statements here, but one takeaway point I would like you to have today is that we have really surprisingly few results on this, where we have taken a spectrum of a supernova and seen emission lines of, for example, neon or magnesium, and said, okay, this supernova produced half a solar mass of magnesium, and this one produced a tenth of a solar mass of neon, and so on. There is very few results on this because it's difficult to do. And one of the reasons it's hard to do is that there is not that many clear lines. If you look in the fourth column here, you see the identified emission lines from each element that we use as probes for the amount that is synthesized in the supernova. If you look at neon here, for example, this is the sixth most common element in the universe, and we have basically no direct determination of its production. And in this case, that is because neon is only showing us one clear spectral line, and it's far over into the mid-infrared region. But so in this field of modeling supernova spectra in the nebular phase, it's basically about trying to understand the luminosities and the line profiles of these different lines, and to connect back to the abundance in the supernova, as well as the morphology of the supernova ejecta. Now we're coming to oxygen soon, and this figure shows you from stellar evolution models how much oxygen you expect to eject if you have a star of a given main sequence mass. So the first thing that's quite striking here is just how steep this dependency is. A 30 solar mass star is expected to produce about 5 solar masses of oxygen, whereas a 10 solar mass star or 12 solar mass star is expected to produce about a tenth of a solar mass. So you have a factor of 50 higher nucleosynthesis yields from these more massive stars. So this sets up a rather interesting situation where you can ask yourself, obviously we have an initial mass function like the salpeter function, that means that these more massive stars are much more rare, but they make so much more nucleosynthesis that it's not entirely clear immediately where most of the oxygen is coming from. Is it coming from a lot of stars making a little bit of oxygen over here, or is it maybe coming from fewer stars but they make much more oxygen per star? And this is something we are going to get back to. The other point I want you to see in this diagram is there is not a unique answer here. I plotted 6 different stellar evolution models, and for a fixed main sequence mass, you see that there's quite a significant spread here, and the spread is typically about a factor of 2. So this is basically when you change your stellar evolution, you make a different assumption about convection, maybe you use different nuclear cross-sections, or you may have rotation or no rotation in the star. You go up and down here by typically a factor of 2 for most of the elements. So it seems like you can do 2 things here. You can, for example, measure the amount of oxygen in a supernova. Let's say you measure 4 solar masses. And then you can say, okay, I will have a little bit of uncertainty here because of the spread, but I can basically determine the progenitor mass. It would be about 27 solar masses. Or you can turn the analysis around and you can say, if I, from some other method, already know the progenitor mass, maybe there's a progenitor image, or maybe there is a very accurate Lycra modeling. And if you knew it was 25 solar masses, and you measure the amount of oxygen, you can sort of pick which one of these stellar evolution models is the better one. So we do this in the nebular phase. What is the nebular phase exactly? It is the phase after approximately 3 or 4 months when the supernova has exploded. What happens then is that the photosphere disappears. You had enough expansion that these inner regions become visible to you. If you're interested in nucleosynthesis, it's actually not that useful to look at the supernova in the first 3 months because you're only seeing the surface layers, and that probes just a very, very tiny fraction of the star. And those outermost layers sometimes don't even contain any nuclear processing layers at all. So we wait until this phase after about 100 days. And then when you come to maybe 2 or 3 years, well, first of all, most supernovae, they become too dim to observe at that time. So you typically don't have data beyond 2 or 3 years. And if you do have data, if the supernova is near enough, typically what you see is something strange happens. Maybe you start to have circumstellar interaction, or you get so complicated physical effects that it becomes difficult to interpret what you see. So this is the range that we usually mean by this term. So typical spectrum looks like this. You see emission lines here. These are spectral fingerprints, each one of different elements, and our goal is to decode this. And the reason we see anything at all, actually, in the nebular phase is because supernovae make radioactivity. So this was back in 1950. It was seen that the supernovae had these exponential tails, and it was a bit mysterious what was going on here. And then Borst said, well, there is only one known process, the physical process that gives you an exponential decay, that's radioactivity. And then it took 20 more years to identify which radioisotope is responsible here. And the answer is 56 cobalt, which in turn is the daughter nucleus of 56 nickel, which is the thing mainly made in this innermost silicon burning region. So we want to determine masses. What do we do? There are sort of 2 different methods that one uses, and often in practice, one is moving back and forth between these, and usually one needs to use both to really get anywhere. So the first one I call inverse modeling, or it's basically nothing more than analytic modeling. You measure line luminosities, and then you have to make some assumption. Maybe you assume that the line is formed in LTE, that is optically thin, and so on. And you have then a nice simple analytic formula that says this is the luminosity as function of temperature and density, for example. Now, of course, the question is, well, what is the temperature and density then? And second of all, that you have made an assumption here that all the conditions are uniform, so you have only a single temperature and density. So of course, you can never really know what you get here, how accurate that is. So we have to always complement this by running simulated spectra from realistic multi-zone models where we have cell-consistent stellar evolution nucleosynthesis and explosive nucleosynthesis. And we treat all the physical processes, and we get the synthetic spectrum out. And I will try to illustrate in the next few slides that there is often this interplay going on where the first method sort of gives you a rough idea, and it identifies which of these multi-zone models you want to calculate. And these advanced models in turn, they sort of feed back into understanding what these analytic methods can actually be used for. So for the second part, the forward modeling, I use a code called Sumo, which I developed for my thesis many years ago. These are the original references here, and it's been gradually sort of improved and polished upon over the years. There are 5 basic ingredients here. To get the synthetic model spectrum out of a supernova, these are the 5 things you sort of need to code up some kind of treatment of. The first one is radioactive decay then, as we said, which is almost always the power source. So you need to include that. You need to have the decay as well as the transport of decay particles. Now these decay particles are typically gamma rays. These gamma rays, they Compton scatter in the ejecta, and this creates a population of semi-relativistic Compton electrons. This is effectively your power source. These MEV electrons, they bounce around and they heat the gas, they ionize it, they excite. They are what makes the supernova emit. So to calculate that, you need to solve what is the distribution of these Compton electrons. So you solve something called the Spencer-Fano equation, which is basically the Boltzmann equation for these electrons. The calculation of the temperature, is necessary, and that is done by having thermal equilibrium condition. Radiative transfer is included in all the sort of modern simulations today. It turns out that even many months or many years into the evolution of the supernova, you can have quite significant effects by line opacity. So these days we do include this part throughout evolution, whereas in earlier modeling, maybe one would really do a nebular approximation and assume that all the emission is optically thin. And finally, the main distinction to the photospheric phases is we cannot assume LTE. We have too low densities, so we have to solve all the rate equations. And what SUMO does here is currently it treats 21 elements between hydrogen and nickel with three first ionization states and maybe a couple of hundred excitation states each. This is currently a 1D code, but there is a way to sort of mimic or to do artificial mixing in the code. Okay, so that was an overview of what the nebular phase of supernovae is, and basically what the modeling approaches are and what the physical ingredients are when you want to make realistic spectral simulations of this. So we come now to 3 applications. The first one is the production of oxygen. This was actually the first applications I did after the code had been completed and tested and so on. So what you see here is in red is an observed spectrum of a type 2P supernova. So this is the explosion of a red supergiant. This is our most common supernova type. And in blue is the model spectrum that comes out if what we have taken here is the Kepler stellar evolution and explosion simulation. So this is a 15 solar mass star evolved with Kepler and then exploded with a piston with 10 to the 51 ergs. And such a star has about 1 solar mass of oxygen in it. Now, depending on your viewpoint, this is a good or a bad or a medium fit. In the sort of supernova spectrum modeling world, this is a fit that one is quite happy with because the physical processes are so complicated and you have so many sort of overlapping lines and so on, that if one arrives to this kind of fit with the model, one is quite satisfied. Now I'll show you this figure. And if you remember the figure I showed you with this oxygen production as function of progenitor mass, it's clear here that when one compares this supernova with the 12 solar mass star that the oxygen lines here are too dim in the 12 solar mass star. There's too little oxygen in such a model to match the observations. And the same holds for magnesium and sodium and other hydrostatic burning products. And then if you go to very high mass, you go to 25 solar masses, here you have 3 solar masses of oxygen. And then you can see how the oxygen line and the magnesium line are really booming here, and you are overproducing that line. So it seems here that we have quite a good diagnostic for estimating the progenitor mass. And the best fit we get if we take something in between here around 15 solar masses. So this is a sort of first natural application of this kind of processing. So we're saying we're not trying to get into improving stellar evolution just quite yet and so on. We're just trying to say, okay, we can have a rough estimate here of the amount of hydrostatic nucleosynthesis. This has a very steep dependency of progenitor mass, so it means that we have a method to estimate the progenitor mass. And you can do this then for a sample of data. Then this figure shows you. Okay, I'll explain a bit carefully here what you're seeing. So you have time on the x-axis. So this is the time after explosion of the supernova. On the y-axis is the luminosity in this oxygen line here at 6300 angstrom. And these tracks here, they are predictions of the model when we change the main sequence mass from 12 up to 25 solar masses. Now, when we overplot observations here, we fill this region down here between maybe something like 10 and 17 solar masses. That is quite good. We know that most supernovae, most core collapse supernovae must come from the sort of 8 to 17 solar mass range. That is just what initial mass function is telling us. But the striking point is that we never seem to have data falling up here. So there seems to be a sort of shortage of massive stars, maybe over 19-20 solar masses. We don't see any observations up in that range. And if you do this with much larger samples, the same picture emerges. So the question arises what this means, what's happening with these massive stars. Are they maybe not exploding as supernovae? Are they becoming stripped envelope supernovae? So if one does the same thing for stripped envelope supernovae, the picture comes out to be the same. So here are the 3 best observed type 2b supernovae that have lost virtually all of their hydrogen envelopes. And also here, we don't see a lot of oxygen production. We see masses of maybe half a solar mass of oxygen, which corresponds, as for the type 2p supernovae, to progenitor masses, maybe 12, 13, 15 solar masses. So some kind of similar helium cores as the type 2p supernovae. The conclusion then seems to be that these type 2b's 1c supernovae, they must have lost their envelopes to a binary interaction. And the reason is that these kind of helium core masses, you don't expect strong enough stellar winds to drive off the envelope. So this links into the question of what is actually happening with massive stars. We certainly see massive red supergiants up to 30 solar masses. We certainly see Wolf-Rayet stars that would be even more massive. This is not the only result that seems to indicate that we are missing explosions of them. Steve Smart produced results about a decade ago that showed that in progenitor imaging, there is also sort of a lack of these massive stars. And maybe today there is the most plausible explanation seems to be that we in fact have failed supernovae to some relatively high frequency once you go to these high masses. Now what you see in this figure here is predictions for whether a supernova explodes, which marks it green, or whether it fails to explode and produces a black hole instead, from this paper by Zuckbold. Now, this is sort of, they have 5 different calibrations methods here, and depending on which one you use, you get different results. But the overall pattern is that once you go over 20 solar masses or so, you start to have these regions where it is really difficult to explode the star. And it seems to be consistent with what we are seeing from these hydrostatic nucleosynthesis yields as well. We are not really seeing evidence for these massive stars on that analysis. So we come back to this important question of where does the oxygen come from? We have oxygen is our 3rd most common element. We should be able to say where it comes from. And I think the current picture is not that clear. What you see here in the blue curve is the relative production per unit solar mass to the total oxygen yield, if you assume that all stars between 10 and 40 solar masses explode as supernovae. And this is what is the normal input into galactic chemical evolution models. And in such a standard JINA-CEE model, most of the oxygen is made by stars more massive than 20 solar masses. You see, you have maybe 2/3 of the oxygen over here and only 1/3 over here. But when we look at oxygen production directly from the supernova spectra, we always end up with results down here. So there seems to be a mismatch then. And there is yet no clear answer to what is the reason for this. Like, why are we not seeing these stars? Is there some systematic error in the modeling and the oxygen mass interpretation? Or is it so that we actually don't have so many supernovae here? And that means that one has to go back and revise these JINA-CEE models. I want to show you one more result from what we can do looking at these emission lines. So what we did here was we tried to estimate the progenitor masses. What about the production of, for example, magnesium to oxygen? So it's been a sort of long-standing issue that most stellar evolution models, they underpredict the magnesium to oxygen ratio by roughly a factor of 2 compared to the solar value. And it's not really clear why this is so, whether this has something to do with the nuclear cross-sections governing this production, or something in the stellar evolution. So what we can try to do from the nebular spectroscopy side is to say, okay, what magnesium to oxygen ratios do we see? And I maybe won't go into the details here, but one can show, and again, this illustrates a little bit that one goes back and forth between analytic methods and the forward models. So in this case, the forward models were used to sort of identify relations like this, to say that the electron density is almost always equal to the singly ionized oxygen density, for example. So you can run a bunch of models and you see that this is always true. And that means that it's a useful relation that you can assume and put into an analytic treatment. And similarly, there is another relation that magnesium tends to be almost fully singly ionized. And then you put these things together and you can derive expressions for certain line ratios that link to certain abundance ratios. And in this method here, we could show that by combining luminosities in oxygen and magnesium recombination lines with these results that were obtained from the forward models, we could derive a method to determine the magnesium mass in the supernova. And in this particular case, a supernova called 2011 DH, we can show that magnesium to oxygen is in fact consistent with the solar ratio. Now, the error bars are approximately a factor of 2, so we are not really resolving this question. But if we can improve the accuracy of this, and we can do it in bigger samples, we should be able to provide input to this and say, well, do supernovae actually make lower or higher ratios than solar, and why is that in case? So I come to my second application, and we are now moving on to explosive burning products, which will be both this and the third application. This one is about stable nickel and what observations of stable nickel lines can tell us about how supernovae explode. So the main diagnostic line is this one shown here. It's at 73, 78 angstrom. Now, again, here I will show you sort of interplay between forward modeling and inverse modeling. So if you compute the spectrum, you use multi-sol models, and you look into the machinery and say, what is happening in the spectral regions? Like which lines are contributing, which elements, what processes are going on here. One thing that falls out is that you can say, well, no matter what kind of model I use, it's always these lines in this region. You know, I don't have contributions by manganese or titanium or some other thing, and it sort of defines the problem. And the model may also tell you, for example, that the lines are forming in a simple way. Maybe they are well into the LTE regime or things like this. And that means that you can link, you measure luminosities, in this case in a nickel 2 line and an iron 2 line over here. And then you use properties of the line formation from your forward models to set up a sort of robust link to the actual abundance ratio, because that's what you want to get to. And without the forward modeling, you are a bit in the dark there, because then you have to assume things that you don't actually know. So it's much better if one can anchor it to the forward simulations. So it turns out that one can measure the luminosities in these two lines. One is from nickel, one is from iron. And there is a very robust link between that line luminosity and the nickel to iron abundance luminosity. Now the nickel comes from stable nickel, 58 nickel, 60 nickel. The iron comes from decayed 56 nickel, because after a few hundred days, all of the 56 nickel has decayed through 56 cobalt to 56 iron. So if you do this a couple of hundred days after explosion, what you're really probing is the production ratio of 58 to 60 nickel versus 56 nickel. So if you measure this in core collapse supernovae, and this table shows you for a few objects that we did, it turns out that the ratio seems to fall into 2 or maybe 3 groups. Most core collapse supernovae give you a nickel to iron ratio that is consistent with the solar value. And then you have a second group where it looks to be significantly higher. You have at least factor 2 or 3 higher than the solar value. And then we have an outlier here, the crab, which has an extreme value, which we get back to. So the picture seems to be that one has a production that is consistent with solar, but it's, if anything, it may be a bit higher. And certainly in some cases, we are definitely a factor few higher than the solar value. So then we can ask ourselves, what does that mean? Why do I sometimes have a solar value? Why do I sometimes have a 3 times solar value? So we try to understand this by doing a follow-up analysis. And what you see here is the results of the nickel to iron ratio when you run an explosive nucleosynthesis network over a parametrized trajectory. So in such a trajectory, you have a peak temperature and you have a peak density. Those are your 2 parameters. And then you follow an adiabatic evolution, which is a good approximation to real supernova simulations. And then you see how much, what is my nickel to iron production ratio for that particular combination. And you can see here, depending on where you are here in peak temperature and peak density, you can get nickel to iron ratios that vary from subsolar to supersolar values. Now, then it's important to look into real 3D supernova explosion simulations and see, well, where are we actually in these parameters then? And it turns out that one is in this middle regime here. This is where you are in peak temperature and density when you look at realistic explosion models. So in this case, if we have a neutron excess of the fuel, so this is how many more neutrons than protons we have, you can produce a nickel to iron ratio that is approximately solar. So you need this neutron excess to make the 58 nickel, the 60 nickel. It has more neutrons than protons, right? Whereas 56 nickel has the same amount of neutrons and protons. So the higher neutron excess you have, the higher you can make this ratio. And to get to the solar ratio, you need to have a value of 0.02. If you raise it factor 3, you also raise this one roughly by a factor of 3. So to get to this sort of second group of observed supernovae, we need a neutron excess that is about 0.006. And now it's very interesting because if one looks at the distribution of the neutron excess in a supernova progenitor model. So here is a MESA model of a 15 solar mass star. And what's plotted here is the electron fraction, which is just 1 minus the neutron excess divided by 2, sort of the inverse of neutron excess. It's a function that decreases inwards, so you tend to have more and more neutron-rich material the deeper you go in the progenitor layers, because you have higher densities, you have more electron captures that increases the neutron excess. And it turns out that at solar metallicity, the oxygen layers have a neutron excess that is exactly 0.02, whereas the next layer, the silicon layer, has a neutron excess that is precisely 0.006. So this means that one could rather neatly explain these two groups by an hypothesis that if you burn this layer, you are going to make the solar ratio, whereas if you burn this layer, you are going to make about 3 times the solar ratio. So if this is correct, it means a very interesting sort of constraint on explosion models. At least sometimes we would need to be able to burn and eject these deep-lying silicon layers. And if so, that is a challenge then for explosion simulations to achieve. I have to flag though for saying this is a quite simplified approach, and we need to see if this idea holds up when we do realistic 3D simulations where this neutron excess is also changed by neutrino processes and so on. What you see here in this figure is the peak temperature and peak density in a 3D model, and the particles over here they sort of retain their original values. They're not exposed to any kind of significant neutrino emission, so they're not going to change their neutron excess. These particles in here, they have been cycled in deep in the convective region just outside the neutron star, and it's possible that you are fundamentally changing your neutron excess here in these layers. And if so, then you would get a different production of these neutron-rich isotopes. But we're not able to do this yet. It's simply not possible to accurately predict this neutron excess in these layers yet because of uncertain neutrino physics. Okay, we come to the my final application. And this is very recent work that just came out last year, and it regards a very surprising and interesting result for supernova 2006 GI. So this is one of the brightest supernovae that we have seen. As you see in this figure here, this is the light curve of the supernova. And if you compare with 1987A, which is down here, or here are some other representative supernovae of the other classes, you see that this really stands out. It's much brighter and lasts much longer than normal supernovae, and in fact radiated about 100 times more energy than normal supernova. It's a type 2N supernova, and what it means is it shows narrow hydrogen lines that are coming from circumstellar material. And we get this kind of spectra when the supernova collides with the circumstellar material, and that is what powers this light curve in this case. So in this particular case, we had a CSM of a mass of order 10 solar masses that must have been ejected very recently before the supernova exploded, approximately a century before. So over the years, we've seen a variety of models to explain this. Pair instability supernovae, LBVs exploding after a giant eruption similar to Eta Carina. It turns out that quite a few model scenarios can sort of give a reasonable light curve here. The common for all of them is that they all involve a massive star. Now, the last spectrum of the supernova was taken in 2009, so this was about 400 days after explosion. And what was interesting here was that there were some emission lines here that we had never seen before in a supernova, and there was no identification of these lines. These are the lines that are marked with blue arrows here. So Kawabata and co-authors, they made some wild guesses here. but none of these are very convincing and are very easy to produce at enough luminosity. And the only thing that could be reliably identified here was some calcium-2 lines, as well as an iron-2 line over here. So these we commonly see in supernovae, but we have never seen these lines here. So it's a real mystery, and it's very rare, actually, that we don't know what the line in the supernova spectrum is. But of course, the fact that we see calcium-2 and iron-2, it seems to suggest that we are probably looking at explosive nucleosynthesis products here. And in this paper from last year, we argued that these lines around 8,000 angstrom, they are very convincingly originating from neutral iron. And what you see in this upper left figure here are the observed lines around 8,000 angstrom in red. And in black is the model spectrum you get if you take half a solar mass of neutral iron, excited to a few thousand degrees, and put it at a typical density, and you get something that matches these lines really well. Looking at the growth trend diagram of iron-1, these lines are in fact one of the most prominent transitions here. They come from multiplet 5 to 2. And you, as long as you have a temperature of a few thousand degrees, you are able to excite this level 5. It has an excitation energy of 2.4 electron volts. And then you are going to decay down here with quite strong lines with high A values. And it turns out that most of the other transitions here, they are either weak optical lines or they are in the infrared. So this is really one of the main signatures of neutral iron. The reason we don't see it normally is that normal supernovae don't have neutral iron. They have ionized irons, iron-2 or iron-3. So there is something in the supernova that made the ionization state quite different and made these lines emerge. Now we modeled the emission, these emission lines, and we tried to put a constraint on the iron mass present in the supernova. And they're really bright, these lines. There's a lot of luminosity here. And it turns out that you can only achieve this if you have quite a significant iron mass. And the limits that we arrived to were between 0.3 and 2.1 solar masses. This is quite significant. Normal core club supernovae that they make 0.1 or maybe 0.2 solar masses, it looks to be too small for this value, and they don't really work out easily for a few other reasons as well. Pulsational pair instability supernovae has been one of the main candidates for 2.6GY, probably ruled out, I would say. There is no 56 nickel production, and there's no way to make these lines in such a model. And the idea that came forward was, what about 1A supernovae? They make about half a solar mass of iron, which seems to fit. And we devised an idea that maybe the supernova arose from a white dwarf that merged with a massive star. And the nice thing that this scenario would explain would be that you could explain why there was an injection of a 10 solar mass CSM just 100 years before a supernova exploded. So you have a synchronization mechanism. If you say that the white dwarf spirals into the companion star, you have a common envelope phase where this envelope is ejected. And then when the white dwarf reaches the center of the companion, it explodes due to the high accretion rates there. So this seems to have a lot of attractive features to it. We tested this. So we ran SUMO. We took a standard 1A explosion model. We decelerated it because this 1A supernova is going to slam into a CSM with at least 10 solar masses. And that means that it's going to lose basically most of its kinetic energy. So you can't have the sort of original velocities. You must have a compression and then deceleration of the supernova. And if you do set up such a model, it turns out that one gets a spectrum out that is in quite good agreement. And in particular, these previously unknown lines come out quite neatly, and they are in fact due to iron-1. We can also show that this bright and long light curve is also in quite good agreement with observations. So all sorts of follow-up questions here if this is the right explanation. I see I'm running out of time, so I will not go into this. Maybe you can ask about it afterwards. I come to the end of my talk. Just want to say one or two words about where we are going and different directions. So one thing we are working a lot on for the moment is to get the modeling capability to 3D. And there is now a 3D version of Sumo in place, and we have, well, some results out. So far we have, with highly simplified microphysics, so we're only doing simple things like emergence of gamma rays, where you have very simple transfer and so on. But here you see examples of line profiles that emerge from 3D simulations from the Gaussian groups. And something very exciting here is to be able to get these kind of line profiles out and compare with observed line profiles. We also made a simplified model for iron lines, and in 87A, for example, the iron lines are quite asymmetric, they're quite broad, and then one can take the current generation of 3D simulations for different viewing angles, which are color-coded here. This is with respect to the neutron star direction. You can see if you manage to get into agreement with this kind of asymmetry or not. So I think I will finish up. This is a summary plot of different elements that we are today sort of diagnosing and having strong results on. That's what you see in green here. In blue are elements where there is potential to get results, but we don't have so many results yet. And in white are elements which are quite difficult to get constraints on from observations. So thank you, and I'll just put my summary slide here.
Thank you very much, Dr. Jerkstrand, for the very nice talk. Are there any questions from the audience? You can unmute yourself and ask, or you can type questions on the chat. Nothing so far. I think I can start then with two questions from a nuclear experimentalist. So have you explored how sensitive are your models on certain reaction rates?
No. So what we normally do is we take our supernova models from the Kepler group, so Stan Woosley and his group, and we have sort of just used their standard models. I mean, they do vary things like the explosion energy, maybe the rotation and things like this. However, I think they have not really produced alternative grids with sort of different nuclear physics and so on. I guess this is one of like many things that one can change. Mm-hmm. And I think the way to do anything there is sort of one needs to first identify a very specific problem or a very specific question, mm-hmm. whether that comes from the nuclear reaction side and say, oh, here is a reaction that we are really struggling with, you know, what impact would it have, or could it even be constrained from observed abundances, or from the other direction, that one sees some particular line ratio or so and has an idea that should depend on something. I don't know, for example, this magnesium production, for example, one could look into how well known is the nuclear physics for magnesium production. So this is carbon burning physics. Mm-hmm. And then maybe play around with that. But I think, so yes, my answer would be there's sort of so many things that one can change around that one has to identify a specific angle on it.
And my second question is, I don't have any experience with these things, but so when you observe the absorption lines from a supernova remnant or something, do you assume that all these ejected materials have been ejected in a kind of symmetric way? Like, for example, what if this oxygen material have been ejected in a weird angle? So when you observe it, you actually see a less intensity, but this doesn't necessarily mean that the amount of oxygen is less, but it's just that there is some attenuation because of their position of these materials relative to the observer. Do you have any?
Yeah. This is a very good question, and in fact, your question sort of summarizes our main headache in in doing this kind of modeling. So I'll just bring up one of my backup slides here. And as you say, you look at the 3D simulations like the one here. This looks not at all like a sort of nice onion shell structure, but something very asymmetric. So we're not, as long as we are doing 1D models, we're not able to get to this. But what we are able to do is that we are able to impose sort of an artificial mixing within the 1D models. So what we do is we take these kind of 3D simulations, we do an angle integral of the distribution of each element. So you get the distribution versus radius for each element. And then that distribution can be mapped into the way we sort of mix things in the 1D setup. So this does not capture asymmetries, will not capture like this blob over here. But this blob would sort of come in and make a tail in a 1D distribution. So it's better than nothing. And in particular, it turns out that the core region of the supernova, if one looks at these angle average distributions, they're very similar for 56 nickel, for silicon, for oxygen. It turns out that all these layers, they're getting mixed very efficiently in the core region by the reverse shock of the supernova. So it's very important to consider this, so we don't put those layers in a sort of onion-like structure where we do mix clumps around with each other in the way that this figure illustrates. But to get to the real asymmetries, we have to pursue the 3D modeling, which we have just started on, but it's still a long way to go.
I see. Thank you. Are there any other questions from the audience?
Yeah, I had a more general question.
Yep.
So if you have underproduction compared to your solar reference, I guess this would mean that you rule out that side for the main production of an element, like for oxygen, for example. But what's the conclusion if you have a overproduction of element like you see it with the nickel? Would that mean you have another effect that decreases it then back to solar, or how would that work?
Yeah, so it depends a little. So when one looks at nickel and iron, both core collapse supernovae and type 1a supernovae are important contributors. Probably they are producing maybe half of the iron and nickel from each channel. So the results that we're showing here was only for core collapse supernovae. And if, let's say then, if we conclude that core collapse supernovae make, on average, they make 2 times the solar nickel to iron, then it means that the 1a supernovae, which is the other channel, they must compensate for this, so they must make half the solar value, right? So that is one wants to arrive at the complete picture. You have to put all the sources, all the contributing sources there, and then for each supernova class, sort of get the result and see if does everything work out. And as you're asking, we have to arrive at the solar values eventually by combining these things. Now it's a bit different, for example, if we look at oxygen and magnesium, because 1a supernovae don't make anything there. So we have to, for magnesium to oxygen, we have to make it by the standard core collapse supernovae. And unless we're completely misunderstood something in the carbon burning layer, we should see a ratio close to this, because this makes the largest oxygen soul mass. So the magnesium to oxygen ratio should be dominated by what we have in the carbon burning ash.
Okay, thank you.
Anders, on the asymmetries, can you say something about the observations that would be diagnostic? Can you work with spectra like time resolved around a few, like between 100 and 200 days or something like this? Would that help you to find out the non-sphericities?
Yeah, so indeed, when we are moving now into this phase of modeling, so we want to compare these kind of line profiles with observations, and normally a supernova is observed in the nebular phase with resolution of maybe a few 100 kilometers per second at the instrument. And what that means is that a profile like this, which is 2000 kilometers per second, it may have 5 or 10 points in it. Like you will resolve this by 5 or 10 bins. It would be better to have more bins. Like let's say you want to really test for the presence of these kind of features, you know, and some explosion models may have them, others may not have them. To be able to do that, you would need data that really resolves this here then down to maybe 100 kilometers per second.
And
so
the
this is
lines would not help.
Sorry?
Optical lines would not help.
Yes, optical lines is sort of the main thing we will work with. You know, there's so much more data in the optical than in the infrared or gamma rays and so on. But
yeah, but I thought of optical lines that are recorded at different times, so that you get this kind of partial absorption of the part of the envelope.
Yes, it's
important
to have the time series as well. Yes, to understand the evolution. Typically, the models don't predict a thing. So much happens on a time scale less than maybe a month or two. So you know, you don't need to observe the supernova every 3 days or every 5 days or something. It's not going to change on those kind of time scale. But on a time scale of maybe 50 or 100 days, you do have this kind of absorption evolution, and it's useful to have time series like that. I didn't include here, as you know, Roland, we also have a comparison of the observed gamma decay lines in 87A compared to these models here, and maybe I should just state what we concluded there. And what we concluded was that current 3D models are still struggling a bit to produce enough asymmetry. We see really strong asymmetry in the gamma decay lines from 87A, and current 3D explosion simulations, they are sort of getting there, but I would say they're maybe halfway there. You know, you need to have even more asymmetric morphologies than what we are currently getting.
Any other questions? All right, if not, then please join me to thank one more time Dr. Jerkstrand for his very nice presentation. Well, thank you very much for accepting our invitation. And I hope to see you everyone in 2 weeks from now in our next online seminar.